Okay, so I welcome you all intellectual adventurers in today's talk. So this in this presentation, I'll talk about numerical methods for linear systems. Okay, so first let me give a brief introduction and motivate you that why you should be interested in studying the linear systems numerically, because so why first understanding the linear systems and then why numerically. So, as we know that linear algebra has ubiquitous presence in physics, so you will see it almost everywhere. So, one obvious place is quantum mechanics. So, let's say um, you have done the variable separation, so that the wave function is only a function of position. Then the Schrodinger equation becomes just an eigenvalue equation. Okay, so for that you need to determine the eigenvalues and the eigenvectors. So so there can be many places where you will need linear algebra techniques, and many times it is possible to solve them just by using paper and pen. But it cannot be always true, because when the size of the system increases, it becomes very hard to solve it on paper. So in those cases, you will need some numerical techniques. So one possibility can be that you want to solve linear systems of equation, and you may also need to calculate the inverse. You may also need to calculate the determinant in some cases. For example, when you consider the case of degeneracy, so when you have the perturbation Hamiltonian present, then the degeneracy may get lifted, so the eigenstates of the system will become different. So you want to calculate those eigenstates, and for that you need to calculate the determinant, and you may be interested in calculating eigenvalues and eigenvectors. Okay, so one example is the rotation matrix. So let's say you have this. So it can happen in either 2D or 3D system, but let me take a simple example of the 2D coordinate system. So let's say this is your original coordinate system, and this is your vector that you were interested in, and you rotate the coordinate system like this. So the red one is the rotated coordinate system with respect to the black, the original one. And then you know that the coordinates of this vector in the two coordinate system would be x, y, x prime, x prime, y prime, etc. Okay. And you also know that these two vectors are related, or the components are related in this way. So say you know what theta is, this theta is, and you know what this x prime and y prime is, then you might be interested in calculating r. Say you know r prime and you know theta, and then you want to know what x and y is. So in that case you will get two equations. So you want to solve this system of equations. Okay, so one possibility can be when you want to understand the electrostatic potentials. So for that case, let's say you have n charges with unknown values. The charges values are not known, but you know where they are placed. So let's say the charge q0 is placed at position r0, q1 is placed at r1, and so on. The charge nth charge qn minus 1 is placed at rn minus 1. Okay, and say you also know that you have measured the potential at given number of points, say n number of points, and then the problem is to find out the values of individual charges. So then this is pretty straightforward to formulate. So because you know that the net potential at any given point, given that the potential is a scalar, you can just add them up. So this is the final value of the potential at any given point, Ri. So then you can set the following system of equations. So for simplicity, because so you can do it in general for any n values, but for simplicity, so that you can clearly see the math or have a feel for it. So let me take the example of n equal to 3. So in that case, you get this system of equations. So here phi 0, phi 1, phi 2 are known, r0, all these quantities are known apart from q0, q1, and q2. So then this system is equivalent to writing, or equivalent to this system. So then you want to solve this system so that you can get the values of q0, q1, and q2. Okay, so this is the problem we want to solve. So this is another place. So now so this is a bit of motivation for studying the linear systems. But then why would you be interested in studying them numerically? So as I said, when the value of n is small, so in this case it was 3, so it might be very easy to do it on paper. But then let's say when n becomes 1000, so how would you solve it? So in those cases, you will need numerical methods, which I will talk about today. Okay. So now the problem statement is that we want to solve this system of equations. Let's say you know all these coefficients. So this matrix is known as the coefficient matrix, and this is the vector b, which you already know, but the unknown is this x0, x1, and or x vector. So you write this system in short form as this. Okay. And then because I don't want to carry around this x0, x1 information, so I'll define something called as the augmented matrix, so which is defined this way. So I'll put all the coefficients of a like this, all the coefficient of b like this. Okay. Now to simplify this system, we can make elementary row transformations. So this is a part of something called as direct methods for solving linear systems, and there are also indirect methods, so which involves iterations. So that I will not talk about today, but in a later talk. So today I'll mostly talk about direct methods, and I will say more about these methods in the forthcoming slides. So these operations, which I call the as the elementary row operations, will only change the coefficients in the augmented matrix, all these coefficients, but it will not change the solution. So as you know, if you have any given equation, say x plus y equal to 5, you can multiply both sides by 10, let's say. So you new equation is 10x plus 10y equals 50, but that will not change the solution. So if you were to solve it, if you were given another equation and you multiply either of the equation by any number, it will not change the solution. So this is the idea behind these elementary row transformations, but then it may help you to simplify the system at hand. Okay. So the final objective is to reach to row reduced echelon form, in which you have, so that means that if you consider this coefficient matrix, then all the entries below upper diagonal or the lower diagonal are 0. Okay. So before going into the details of the method, let me also talk about elementary row transformations, because I will use these operations over and over again. Okay. So there are three elementary row transformations. One is a scaling, in which you multiply a given row by a given number. So let's say here I have multiplied the jth row by scalar lambda. So this is the matrix that you should multiply the augmented matrix with. So if you do this, the jth row will be multiplied by the lambda scalar. The other one is pivoting. So pivoting means that you want to interchange any two given rows. Okay. So let's say if you want to interchange Ri and Rj rows, then you perform this elementary row transformations, and it has also a very specific form of the matrix. So you multiply this matrix with the augmented matrix and you get your row interchanged. And the third one is elimination. So you perform this elementary row transformation in order to introduce zeros. So we will talk about this when we talk about Gauss elimination. We'll talk about that. So these are three basic elementary row transformations that you will use in order to reduce your system so that it becomes simple, and then you can solve it. Okay. So now let me give you a brief summary of various solving strategies. So there are basically two strategies. So one are so-called the direct methods, the other are the indirect methods. So in the case of direct methods, we transform the given system into a simpler system that is easily solvable. So there can be many methods, but we will talk about the backward substitution or the forward substitution, Gauss elimination, Gauss-Jordan elimination, and LU decomposition. So you may have heard of Cholesky decomposition. So that's a special case of LU decomposition. So these are the direct methods in which you modify the system at hand, but there are also indirect methods in which you start with a solution. You start with a guess solution and then you try to improvise it over the iterations. Okay. So these methods are usually applicable for the banded matrix. Then for the banded matrices where most of the elements of the matrix are 0. Okay. So it will converge very fast in those cases, and it is usually used in those cases where you have banded matrices. Okay. So some of the iterative methods are Jacobi method, Gauss-Seidel method, and so successive over relaxation is a way of improvising this Gauss-Seidel method. So We will not talk about indirect methods today. We will talk about them in some other talk. Okay. So first, okay, because I will need this notation over and over again. So let me also introduce. Perhaps you know it already. So let me also introduce to the big O notation, because whenever you do, this is usually very used in theoretical computer science. But let me introduce you to it anyway, because you will need it. So the big O notation is used. So big O notation gives you the kind of order of magnitude of calculations that will be done when you perform a given algorithm. Okay, or it may give you the complexity of the algorithm. So you may have you may want to solve a problem, and then there are two ways of doing it. So let's say one of them scales as n cube, one of them scales as n power 4. So then we will choose this method, because this scales. So when you increase n, the number of operations that you will have to perform in this case will be smaller as compared to this case. So we will count something called as flops, or the floating point operations. Okay. So just to give you some feel for it, so the usual computers have number of flops at 10 power 12 or teraflops. So let's say my system maybe has, because it has one Intel processor, so it may have capability of about 10 power 12 flops per second. But then if you contrast it with the world's fastest supercomputer, so that has 10 power 18 flops per second, but then it comes with a price. So these sort of systems, when I talk about this supercomputer, it consumes about 22,000 watts. So it means that for every hour you run this system, you will make 22,000 units. So this comes with a price. Computing definitely comes with a price. So let me give you some examples of order of magnitude of calculations of order of magnitude of the number of computations or the flops. So for example, when you consider product, or when you calculate factorial and factorial, so then you multiply. So let's say you have 3 factorial. So what you will do? You will do 1 cross 2 cross 3. So then you have to perform 3 multiplications. So first you multiply 1 by 2, and then you multiply the result with 3. So thus, for n factorial case, you have to do multiplication n minus 1 number of times. So for when you say that n is very large, n minus 1 is approximately equal to n. So you say that the problem scales as O(n). Is this okay? So the same thing will happen when you sum to n digits. So let's say you have 1 plus 2 plus 3 plus 4 plus 5. So when you sum to 5 digits, you have to perform 4 additions. So first 1 plus 2, then you add it to 3, then you add it to 4, then you add it to 5. So in total you perform 4 additions. So some more examples are that when you multiply 2 matrices, 2 n cross n matrices, then you have to perform 2n cube minus n square number of operations. So this scales as O(n) cube, and so on. So we will kind of discuss this complexity calculation for other algorithms like Gauss-Jordan elimination and Gauss elimination. So first method that we'll talk about is the backward substitution. So perhaps the name itself should give you some insight that what are we going to do in this case. Okay, so although this might seem a bit artificial, because many of the systems will not come in this form. Okay, so first let me say that the backward substitution is applicable in those cases when you have upper triangular matrix. Okay, so upper triangular matrix, as you all know, satisfies this condition. So because eventually we are going to use backward substitution in Gauss elimination, so it's worthwhile to discuss backward substitution anyway. Okay, so the method of forward substitution that we will use eventually in the LU decomposition, I will talk about that later. Okay, so this is the algorithm. So let's say you have this upper triangular matrix in which the entries below the diagonal are 0. So these are 0, and let's say you want to solve the system, and let's say, as I said before, these numbers are known. So it's very easy to solve. First you solve for x2, which is this. Then you backward substitute it for in this equation for x1, then you know x1, and then when you know x2 and x1, you can know what x0 is. Okay, so this is how it is implemented. And then also, so for the general case, you have to perform the values given by this. So first you perform the last one, and then you keep coming back, and in the last you compute x0, the first element. So this is what the index is saying. First you compute the last, this one, then you come back, further, then you go to the last one, go to the first one. So this is how you solve this system of equation. Okay, and this can also be very easily implemented in the in a Python code. So okay, so if time permits, I will also discuss the Python codes later. So first let me talk the theory part, and then I'll explain the various algorithms. Okay, the next is scaling calculation. So in this case, as you have seen that, like for example, here you need to multiply some numbers, and here you need to subtract them, because you have to perform this calculation for all these numbers. So, and you can show that this backward substitution requires n square minus n over 2 additions, and n square plus n over 2 multiplications or divisions. So that's the total number of flops, or the total number of floating point operations is n square. And then, so you would say that this problem scales as O n square. So if you do it for let's say 100 cross 100 matrix, and if you do it for 1000 cross 1000 matrix, so 1000 cross 1000 will take about 100 times more time, 100 times more amount of time as compared to the n equal to 100 case, because it scales as O n square. So that gives you the kind of time the algorithm will take for computation. Okay, the next is Gauss elimination. So maybe you have seen it, or you have actually used it in some particular cases, or at least for 3 cross 3 cases, because you will be familiar, although you may not know what is the name, but you will be familiar with this method. Okay, so the method we talked about, so the method we just talked about was backward substitution. So that is applicable when the matrix has an upper triangular form, but this is not what happens in reality. So the matrix need not be upper triangular, the coefficient matrix need not be upper triangular. So thus this, in that case, we use Gauss elimination. So Gauss elimination involves the transformation of the given matrix A that we dealt with a given number of times, and I will show what is the meaning of transformation. So first part of the transformation is the elimination phase, where you introduce as many zeros as you can, because you want to convert your system, the coefficient matrix, into an upper triangular form. And after that, when you get the upper triangular matrix, you will perform the backward substitution, as I just discussed. Okay, so these are the two important parts that are involved in Gauss elimination. So let me give you an example of this. So let's say you have this system of equation. So first you will convert this into an augmented matrix, and then you perform the various elementary row transformations, and then eventually you will get an upper triangular form, and then you can use the result that I showed before for the backward substitution, and then you first solve for x2, then for x1, and then finally for x0. Okay, so I think the solution for this would be 3, 2.5, and 7. This is what I remember, but you can check. Okay, so now very important part is the scaling calculation. So how does the problem scale? So for estimating flops, we divide the task into two parts. So as I said, that the Gauss elimination consists of two parts. So one is the elimination phase, the other one is the backward substitution. So then if you do all the math carefully, then you can show that the total number of computation you need for n cross n matrix. So this is the worst case. Okay, you can have your you can make your code more efficient by introducing some conditionals, that the computation need not be done when such condition arises. But I'm talking about the worst case scenario. So in the worst case, you have to have these many number of computations. So it scales like this, 2n cube over 3. So so let's say you have a system in which you had the matrix 100 cross 100, and then for the other system you have 1000 cross 1000. So if the scaling is like that, is like this, then it means that it will be uh, about 666 times slower. So it will take about that much amount of time. So let's say if your 100 cross 100 system was taking 1 second, then 1000 cross 1000 system will take about 670 seconds. So this is how it scales. So by knowing this, by knowing the scaling, you can know a priori. Of course, this is theoretical computation. You can know a priori that whether you need a supercomputer, whether you need an upgraded hardware for your computation or not, because not every time your system will be able to do computation for any given value of n. Okay, so now you can also compare it with naive elementary row transformations, because that will involve multiplying matrices together. Okay, but that has even bad scaling, even worse scaling. So that goes as n power 5. So we will not use this. Okay, so since this is extremely wasteful, so we will not use this method. We will only be dealing with the Gauss elimination. Okay, so a variation of Gauss elimination. Okay, so before I proceed, do you have any questions? Any questions? Say either yes or no, so that I can be sure that you are still online.
No.
Okay, fine. I'll proceed then. So the second one is Gauss-Jordan elimination. So this is sort of variation of the Gauss elimination process. Okay. So in this case also we perform elementary row transformations, but the final result that the coefficient matrix becomes, in this case it becomes an identity matrix. Okay. In contrast to the previous case where we obtain an upper triangular matrix. So there is a difference in this case. In this case, therefore, that after, so in the Gauss elimination method, you have to have backward substitution after you get the upper triangular matrix. But in this case, you don't have to perform the backward substitution, because you will eventually get an identity matrix. So what I mean to say, that if you start with any coefficient matrix A, after performing elementary row transformations, you will eventually get an identity matrix. So then you don't have to perform backward substitution. Okay. So in this case, the floating point calculations or number of flops is O n cube. So this is worse than Gauss elimination. And this is understandable because you are trying to introduce 1 on the diagonal. So because in the previous case, you had upper triangular matrix, but in this case, you will have a diagonal form. I mean, no, not just diagonal, but ones. So that's why it is wasteful. Okay. So we usually don't use Gauss-Jordan elimination, but maybe sometimes you may need this. So there are some places. So I'll talk about this. So you can apply the Gauss-Jordan elimination on this system. Finally, this will be reduced to, so this becomes an identity matrix multiplied by x0, x1, x2 equals this, equals some coefficient. So then you can solve them directly. Okay, so now let me make a comparison between Gauss and Gauss-Jordan elimination. So first thing is, first attribute is number of flops. So Gauss elimination scales like this, and Gauss-Jordan elimination scales like this. So this is pretty much wasteful, because this takes about 50% more number of flops, this process. So we usually use Gauss elimination. And the final result after elimination gives you upper triangular matrix in the case of Gauss elimination, but in this case the coefficient matrix becomes an identity matrix. So that's why you don't have to back substitute. So for the Gauss elimination, you will eventually have to perform back substitution, but this is not needed in the case of Gauss-Jordan elimination. So you may say, okay, so maybe Gauss-Jordan elimination is a wasteful process. So maybe it's not used anywhere, but that's not the case. So this method can be used to produce matrix inversion program because of some reasons. I mean, I'm not so sure, but then if you're interested, you can read this book. So I'm also giving the page number. So if you're interested, why how it is done, so it's given on page number 523. Okay. Okay. So the next is the LU decomposition. So this is the final, the last method that I will talk about as the direct method. So in the future talk, I'll talk about indirect methods. Okay. So so a brief introduction. So the Gauss elimination method is a robust method for elimination when you want to solve a system of linear equations like this. So let's say in some cases when you have to change this B coefficient or this matrix on the RHS again and again, you need to perform the same Gauss elimination again and again. So which is very wasteful. So then what you do in those cases, you try to store the operations that you performed on A in some way that I will talk about, so that you don't have to perform all those elementary row transformations on the coefficient matrix. So this is the basic idea behind LU decomposition. Okay. So let's say, so I will of course say some words about when can it be done, how it is done, and so on. So first, let's say that you are able to perform LU decomposition. So what are the advantages? Okay. So let's say oh, this should be AX. Oh, sorry, there is a typo here. This should be AX equal to B. Okay. So assume that you can perform the LU decomposition and then you can write A as LU. So this should have been A. So then you will get LUX equals B. Okay. And assume that Ly equal to B. So this thing where Ux is equal to Y. So now what you will do, since you know what B is, since you know what L is, you first need to determine Y. And then once you know Y, you can determine X. So this is also very systematic. So let me repeat that. Let me repeat the algorithm. So this is the algorithm. So let's say you have the system AX equal to B. Then you write A as LU. It says that you have performed the LU decomposition. So that you will write this equation as this one. In this way, LUX equal to B. And then you say that Ly equal to B and Ux equal to Y. So first you have to solve then for Y, because you know both B and L through forward substitution, and then you use that solution in here because you know what Y is, and then you can know X. So it's done in 2 stages. Okay. So now the LU decomposition will involve 3 steps overall. So first you need to find out a way of making the LU decomposition. First is that. The second one is you have to perform the forward substitution, and then you will make a backward substitution. So these 3 steps are involved. Okay. So now the LU decomposition. So let's say in the present case, we are dealing with non-singular matrix. Of course, if you deal with singular matrix, then the story is completely different, because in those cases you may have or may not have solution depending upon what B has the values. Okay. Okay. So first thing that I must say here is that that this decomposition is not unique. Okay. So this decomposition, when you write A as LU, this is not unique. So in order to make it unique, you have to make some assumptions. Okay. So one case of so one possibility is that you do a Doolittle decomposition. So that means that for this matrix L, all the diagonal elements are 1. So if you do that, then the decomposition becomes unique. There are no 2 decompositions in that case. The other possibility is a Cholesky decomposition. So in the Cholesky decomposition, you take the same matrix, and instead of U, you will take A equals L transpose. Okay. So Cholesky decomposition is applicable when the coefficient matrix is symmetric. Okay. and it also must satisfy some other properties. So let me give an example. Okay, so let me give an example of the duality decomposition. So let's say, so this is what we are doing when we want to calculate the LU decomposition. So in order to understand how it can be done, so first observe this. So let's say we have already solved this problem and then have found that this is the decomposition of A in terms of L and U. Okay, so as I said, for the duality decomposition you have 1 on the diagonal. So if you multiply these together, you will get this matrix. Okay, so now if we perform the elimination as we did in the case of Gauss elimination, then this matrix becomes this. Okay, and the coefficient that you will use, the coefficient lambda that you will use for making this transformation are actually these coefficients. So then you know that how are you going to get the LU decomposition. Okay, so this is the algorithm for making the LU decomposition. So start with any given matrix A, perform the elementary row transformations, and then but you keep track of all the coefficients that you have used for elimination. So finally you will reach the upper triangular matrix, and the coefficients that you got in between will give you the lower triangular matrix. So this is the algorithm for implementing this, and this can be generalized to n cross n case. So here I have shown the example for 3 cross 3, but then this can be generalized to n cross n case. Okay, so now so what I will do now, I will summarize direct methods and I will explain some of these algorithms. I'll explain the Gauss elimination and also the backward substitution through a code, okay, through Python code. So let me first summarize the direct methods. So direct methods have so first direct method that we talked about was substitution. So it had forward substitution and backward substitution, but then these are the very special cases when the matrix you have very specific form. So for forward substitution you have lower triangular matrix, for the backward substitution you have upper triangular matrix, and those will also be used for later as I talked about in Gauss elimination. So yet another direct method was Gauss elimination. So you in this method you have two stages. So one is elimination, where you try to perform the elementary row transformations so that the system you are looking at becomes simpler to solve, and this is followed. So this makes the system upper triangular, or the coefficient matrix upper triangular, or the system as the row reduced echelon form. And then you finally perform this backward substitution, and then you can solve the system. So the one of the variant was Gauss-Jordan. So the difference was there in that, of course, key first is that it is expensive method as compared to the Gauss elimination. So this all, so and also as a final result you will get the identity matrix instead of the Gauss elimination, in which you get the upper triangular form. Okay, so so that's why you don't have to make a backward substitution as you do in the case of this Gauss elimination. Okay, so the final direct method that we talked about was LU decomposition. So there can be variants. So one possibility can be crowd decomposition, which we not talked about, but for example, if you have the matrix that is symmetric, then you may prefer the Cholesky decomposition. But if it's not, then you perform the duality decomposition, because if you make some assumptions, then it becomes unique. Otherwise, it's not. So duality decomposition will also make it unique. So in that case, you try to have all diagonal entries equal to 1. So what was the algorithm that we discussed? That you start with the matrix A, and then you apply elimination. You take care of all the coefficients that you used for elimination, and then you will eventually get the upper triangular form, and the coefficient will become the part of lower triangular matrix, and then you perform the backward substitution and forward substitution, and you will get your matrix. Okay, or rather you will get your solution. So this was the case with direct methods. So let me also explain the things with some examples. So I'll stop sharing this and I will again share my desktop. Okay. So let me open the Jupyter notebook for you. So this is the code that I've taken from this book, this book, Numerical Methods in Physics, and this is the author. Of course, I've made some changes in the code in order to make it more useful for us, for my purpose. So okay, so this is the case of backward substitution. Okay, so in order to appreciate what actually is happening, let me show the algorithm, the math of it, and how it is implemented side by side. So what is being done here is, so focus on this part. So you look at line number 18, this line, and you compare it with this line, xi and this one. So what? So it is dividing by uii, it is dividing by uii, and then it is first summing over this. So sum is being performed here. Okay. So sum is effectively uh, a multiplication between a given row and this vector. Okay, so you know some values already, and then you multiply it with the vector to in order to get to the other solution. So let's say you know what x2 is, what x1 is, then with the help of that you will know what x0 is. Okay, so this is what you are doing here. So this multiplication here is denoted by at, which is here, and then you can make one-to-one correspondence with the result that with this and this. Okay, so and here actually you can see the matrix. So let me give an example now. So let's say, so let me make some system. Okay, so let me make a simple system. I'll put say 5 here. So and let me run this code now. So this is the matrix, this is a coefficient matrix which I'm trying to solve, and the matrix B is, so let me also print the matrix, print, and this is the B matrix. Okay, so this is this matrix, and I'm trying to solve this system. So when I try to solve the system, so using backward substitution, because, oh sorry, I'm sorry, 1 minute, I need to make a change. Now it's fine. I've made some changes in this. Anyway, so first let me talk about what how would I use the Gauss elimination. Okay. So when you use Gauss elimination, you can see that these are the numbers given by the Python inbuilt libraries, and this is the method that we obtained using Gauss elimination. So first, wait, I need to make some changes to it. I made some changes because okay, so sorry, the code is not available with me right now because I need to first convert this to an upper triangular form, then only it will work. So let me check whether I have it or not. So a equals np dot okay, so I'm not able to recall the exact method that is used for making, for extracting the upper triangular matrix, but then you can see that the Gauss elimination works really well. Okay, so yeah, that's it. So today I have talked about this. So in the future talk, I'll also talk about the indirect methods. Okay, so this is all I have to say about today. So if you have any questions, you can ask them now.